So the very first chapter of Crossing the River with Dogs deals with the problem-solving strategy of drawing a diagram. Diagrams are often the key to getting started on a problem. They can clarify relationships that appear complicated when first written. Problem solving often revolves around how information is organized. When you draw a diagram, you organize information spatially, which then allows the visual part of your brain to become more involved in the problem-solving process. So what we're going to be doing is we're going to be drawing diagrams for every single problem that we do in this chapter. Yes, there are other ways to solve them, but we're going to work on sharpening our diagram drawing and solving skills in this chapter. So the very first problem that we're going to look at is on page 12. It's called the Virtual Basketball League. And quite frankly, that's the only type of basketball that is going to be played right now, given that the NBA season was shut down. At any rate, the problem reads as follows. Andrew and his friends have formed a fantasy basketball league in which each team will play 3 games against each of the other teams. There are 7 teams: the Texas A&M Aggies, the Purdue Boilermakers, the Alabama Crimson Tide, the Oregon Ducks, the Boston College Eagles, the Air Force Falcons, and the Florida Gators. How many games will be played in all? So the very first step is organizing the information here. And so we want to be attentive and eager to set up a system here. What are the key elements? A, there's 7 teams. Each team is going to play the other team. So you have to determine how many unique games take place. Then after we determine how many unique games there are, we have to realize that there are 3 of those games being played. So those are the critical pieces to this problem. When you read this problem, I do think that the diagram approach immediately comes to mind, and you think of, writing each of those 7 teams, maybe representing them with a dot and labeling as I did with A through G. You could also just write the names and forego using letters A through G. But if you draw a line from each of those points to another, they would represent a unique game. So if A represented Texas A&M and we drew a line from A to B and B represented the Purdue Boilermakers, that would be the game between Texas A&M and Purdue Boilermakers. And then A to C would be between Texas A&M and Alabama Crimson Tide, and A to D would be between Texas A&M and the Oregon Ducks, and so forth. So you have that Texas A&M is playing 6 unique games, and you see that 6 written in step 3 up with A. Now, when I go to B and I consider all the unique games that the Purdue Boilermakers will play, I have the number 5 in step 3. Why? Because there's already a line extending from A to B. That's the game between Texas A&M and the Purdue Boilermakers, and it was already accounted for when I drew the lines for all the unique games that Texas A&M would be playing. So there's 1 less unique game as there's 1 less line segment being drawn. And then when you go down to C and you draw each line segment, there's going to be 2 less because you will have already connected B to C, and we already had, when we drew A's lines, A to C, and so forth. And that pattern would continue until you get down to the Air Force Falcons, and you're only going to draw 1 line. So when you get up to the Florida Gators, which is represented with a G, there are no lines left to draw. So the number of unique games would be found by summing together the 6 plus 5 plus 4 plus 3 plus 2 plus 1. That gives us 21 individual unique games. Those are each played 3 times, so we multiply by 3 and we get 63 total games. If you need a little bit more visual assistance with this and also narration, you can turn to page 14 and 15 of your text, and it goes through this in more detail. The next problem we're going to solve is the model train problem on page 15. It says Esser's model train is set up on a circular track. 6 telephone poles are spaced evenly around the track. The engine of Esser's train takes 10 seconds to go from the first pole to the third pole. How long would it take the engine to go all the way around the track? What I would encourage you to do before you go to the next slide is take a moment and draw what you think this diagram should look like, as that helps to sharpen your diagram drawing skills. So here is my model. The inner circle with the 6 dots represent the 6 telephone poles in the actual track. That outer loop just indicates the time that it takes to get from one telephone pole to the next one. So you have your 6 poles. They're evenly spaced, assume they are. We're told that to move from the first to the third, it takes 10 seconds, and that same pace is maintained. So from the first to the third, 10 seconds. That means from the third to the fifth, it's going to take another 10 seconds. And then from the fifth back to the first, a final 10 seconds. So that would be 10 plus 10 plus 10, 30 seconds total to make it all the way around the track. I think a common mistake could be just going to the 6th light pole and not realizing you have to finish that loop by going from the 6th back to the 1st and getting back to the starting place. And so you could potentially just say 25 seconds, but that would not be closing that full loop and moving all the way around. So again, the total is 30 seconds. The next problem that we're going to explore is the pool deck on page 17. It reads as follows. Curly used a shovel to dig his own swimming pool. He figured he needed a pool because digging it was hard work and he could use it to cool off after working on it all day. He also planned to build a rectangular concrete deck around the pool that would be 6 feet wide at all points except the corners. The pool is rectangular and measures 14 feet by 40 feet. What is the area of the deck? Now, drawing this diagram might come really easily to you because I feel like this type of diagram is really prominent in early geometry classes as well as on like the ACT, where you have to draw 2 rectangles, one inside and one externally, and then figure out just the area of the walkway around it. So your pool measures 14 by 40, so you're going to put that in the inside, and then you're going to draw a 6-inch perimeter around the entire thing. And then what we need to do in order to find the area of just that walkway that's around it is to find the area of that larger rectangle and then just subtract the area of the pool. That would be one way. Yes, you could go around and find the area of just the rectangular portions of that walkway. You would have to be certain that you don't include any overlapping parts. That's why I think the most efficient way would probably be just to find the area, to subtract the 2 areas of the entire outer rectangle and then that of the inner pool. But at any rate, you have the inner pool, no big deal. Then you add that 6-inch perimeter around, and that you have to then use to find the area of the full pool, including the walkway around. So you have 6 feet added to in 2 directions to the width and in 2 directions to the length. So you really have 12 feet being added on. So when you add the 12 feet to the 14, you get 26 feet. And when you add the 12 feet to the 40, you get 52. So overall, you have a 26 by 52 outer rectangle and then a 14 by 40 pool. So that outside area of the pool and the concrete deck or walkway would be 52 by 26, which is 1,352 feet. And then our pool, which has an area of 40 by 14 or 560 feet. We take the difference and we get that the footage of the deck or the concrete area around the perimeter is 792 feet. The last problem we're going to look at is called Farmer Ben, and it is on page 19 of your text. It says Farmer Ben has only ducks and cows. He can't remember how many of each he has, but he doesn't need to remember because he knows he has 22 animals and that 22 is also his age. He also knows that the animals have a total of 56 legs because 56 is also his father's age. Assuming that each animal has all legs intact and no extra limbs, how many of each animal does Farmer Ben have? Your initial hunch might be to do some algebra here. I ask you to resist that and try to draw a diagram for this. So what would a diagram look like for this? Well, you all know my minimal drawing capabilities, and it's mimicked by what they have in the text, which is on the screen. So what I would say to do is start out with all ducks, because if you have all ducks and you know that you have 22 animals, that would be 44 legs. Now he knows he has 56 legs, so if you draw just some heads and draw 2 legs per each to indicate ducks, that gives you your 22 animals, 44 legs. And then just add 2 more legs per little figure there. Of course, they look like they were some octopi that were in a tragic accident and only have 4 legs left. But at any rate, those would represent your cows because they would have 4 legs each. Keep adding until you hit that total of 56 legs. So you're adding 2, 2, 2, 2, 2, 2 until you hit 56 and you realize, oh, okay, I'd have 6 with 4 legs being my cows, 16 animals with 2 legs being my ducks. That's how you would solve it with a diagram. Of course, you could easily do an algebraic model for this as well. You know that ducks plus cows is 22, being equation number 1, and that if you know total legs is 56, if you take number of ducks multiplied by 2, number of cows multiplied by 4, that would be your second equation. And then from there, you could solve by substitution or linear elimination. Since the emphasis of this chapter is diagrams, I want you to focus on being able to draw a diagram. So, in summary, diagrams are important. Research really does show that most good problem solvers draw diagrams for almost every problem they solve. It's a great cross-check. It also really empowers you spatially and visually. And really, any idea that can be represented with a picture, it can be communicated more effectively with that picture. So as a teaching aid, it's really, really important to be able to draw diagrams when you can. By making visible what a person is thinking, a diagram really does become a powerful problem-solving strategy. To practice your own diagram drawing, I would like you to try problems 1, 3, 4, and 11 on pages 21 through 23. I will go through some solutions for these in a separate PowerPoint. Then I'm going to ask you to also try some other problems independently, and I will provide those answers at the beginning of next week. That way you have ample time to give them a whirl.